So we will now look at more examples of an algorithm design strategy called divide and conquer. So in divide and conquer, what you do is you take your problem and you break it up into parts, typically into two parts which are disjoint, which don't refer to each other. Then you solve these parts separately and then you combine the solutions efficiently. So a typical example of this is merge sort. So if you remember in merge sort, we break the list into the first half and the second half. So imagine in the TA situation that you have two TAs, so you can give each of the TAs one half of the papers to sort. They don't have to refer to each other, so these problems are disjoint. And then when the TAs bring the sorted papers back, you have to merge them. So that is the step of combining the disjoint subproblems. So you create these disjoint solutions and then you have to combine them, and you have to do that combination efficiently to make sure that you have got the benefit of doing this. So quicksort was also a divide and conquer algorithm. The division process was a little more complicated. We did not just take the midpoint of the array or list and split it. Rather, we split the list based on a pivot. So we created a lower partition and an upper partition. So it took a little bit of effort to split them. And then to combine them, the lower partition sits below the pivot and the upper partition sits above the pivot. So you combine them by just placing these two partitions with respect to each other correctly around the pivot. So these are two examples of divide and conquer, and now let's look at another problem. So the first example we are going to look at is motivated by something called a recommender system. So when you log into an online website, typically an e-commerce site, you get some recommendations. Now it could be e-commerce, it could also be an entertainment site like Netflix. So you are told that here are some shows that you might want to watch. So of course some of these are based on your own past history, but a lot of the recommendations are based on the histories of people which the system believes are similar to you. So the recommender system tries to compare your profile with the profile of other customers. So how do we do this? Well, we have to somehow identify other customers who have similar likes and similar dislikes, and based on this, the recommendation believes that if somebody else likes similar things to you and they have liked something subsequently which you have not seen, then it should be recommended to you. So our task is going to be related to this question of how to compare profiles, right? So how do you compare one customer against another customer? How do you find out whether this customer is similar to that? Well, the assumption is that these customers over time have given some ratings or rankings. So it essentially boils down to checking your likes and dislikes, which is the same as comparing the rankings that you give with the rankings that somebody else gives. So let's look at comparing rankings. So supposing there are 5 movies that you and a friend have both seen. Let's just call them A, B, C, D, E. So your ranking is that D is the best, B is the second best, then C, then A, then E. And on the other hand, your friend thinks B is the best, then A, then C, then D, then E. So there are many ways to compare such rankings, but one of the simplest ways is to just look at each pair of movies and see whether you and your friend agree on how they should be ranked relative to each other. So for instance, if you look at B and C, then both you and your friend agree that B is better than C. So you agree on the relative merits of B and C. On the other hand, if you look at D and B, right? So here you believe that D is the best movie overall and hence it's better than B, whereas your friend believes B is the best movie overall and in fact ranks D quite low. So we are not really concerned about whether D is very low or not compared to B. We are just concerned about the fact that you prefer D to B and your friend prefers B to D. So this is one point of difference between you and your friend in terms of preferences. So in this way you can do it for every pair of movies and see how many movies you agree on, how many pairs of movies you agree on, and how many pairs of movies you disagree on. So essentially what we are looking for is some measure of this disagreement, right? So we are looking for these inversions in preference. So where you prefer say D to B and your friend prefers B to D. So this means this is a pair over which your preference with respect to your friend is inverted. So clearly if every pair is the same, for every pair of movies if you and your friend agree on the relative ranking, you can think about it, there is no way that your overall ranking can be any different. So if all pairs are equal, that is there are no inversions, then you have identical tastes. On the other hand, if you disagree completely, this means on any pair of movies where you think one is better than the other, your friend thinks the opposite. So if every pair is inverted, then you are maximally dissimilar. You cannot be more different from that from somebody else in terms of tastes. So the minimum number of inversions that you can have between two people in this is 0, right? They agree on everything. The maximum number is that they disagree on every pair. So every pair among n elements is n into n minus 1 by 2. So the number of inversions ranges from 0 to n into n minus 1 by 2. So 0 means minimal, that is they are exactly identical. N into n minus 1 by 2 means they are maximally dissimilar. So this gives us some measure. So now remember, our goal in this recommender system was to say that one customer is similar to another customer. Right? So what this number is giving you, the number of inversions is giving you, is the opposite of similarity. It's giving you dissimilarity. So obviously if something is more dissimilar, it is less similar. So you can just invert this and say that people who have a low inversion number are very similar, and those who have a high inversion number are not very similar. So it's a bit of a nuisance to work with this A, B, C, D, E and to look at two different sequences and compare them for inversions. But we don't really need to think of them as two different sequences because we can fix one as a reference. So for instance, we can take your sequence and renumber or rename all the objects to be 1 to n in the order that you prefer. So the other person now has a different ordering. If their ordering is also 1, 2, 3, 4 up to n, then they have an identical ordering, there are row inversions. But in general, with respect to your preference, this is my movie 1, this is my movie 2 and so on, there will be a different order that the other person gives, which will be effectively a permutation of these numbers 1 to n. So in this situation, it's now easy to describe what an inversion is. So as far as you are concerned, the odd numbers should be in ascending sequence, right? So the higher numbers have lower preference for you. But if they are inverted, then it means that a higher number has come before a lower number. So you have an I which appears before j in the sequence, okay, but actually I is bigger than j. So this is how an inversion appears. So as we said, the number of inversions ranges from 0 to n into n minus 1 by 2. So they could be order n squared inversions. And our goal is to determine this dissimilarity. So we want to actually count the number of inversions in order to give a number to this, to quantity to this similarity between two people. So let's say that your ranking as before is DBCAE. So as we had said, we will renumber these things as 1, 2, 3, 4, 5 in that sequence. So 1, 2, 3, 4, 5 represents now the new naming or numbering in the order of preference that you have. And now if you look at your friend's preference, which is BACDE, then correspondingly the numbering becomes 2, 4, 3, 1, 5. So now we want to see how many things are inverted. So effectively it means looking for each number, how many things which are smaller than that number come before it. Or alternatively, for each number, bigger than that number come before it. So for example, if I look at 1, right? So I want to see how many numbers which are bigger than 1. Everything bigger than 1 should come to its right according to our thing, but anything that is to its left is an inversion. So 2 is an inversion, 4 is an inversion, 3 is an inversion, because these are all, 1 is the smallest number. What about 2? Well, if I look at 2, then to its left there is nothing. So there is no number which is inverted with respect to 2 in this sense. What about 3? Well, in terms of 3, 2 is before 3, but 2 is smaller, so it's fine. But 4 is before 3 and this is an inversion, right? 4 should come after 3. What about 4? Well, for 4, the only number before it is 2, which is smaller than 2, so they are in the correct order. And finally for 5, which is the biggest number, everything is before 5, so there are no inversions. So in this, if you remember, we got 3 inversions for 1. We got 1 inversion for 3 and nothing else. So the total number of inversions in this is these pairs. So 1 and 2 are inverted because they are in the wrong order. 1 and 3 are inverted because they are in the wrong order. 1 and 4 are inverted because they are in the wrong order. And 3 and 4 are also inverted because they are in the wrong order. Every other pair is in the correct sequence with respect to your 1, 2, 3, 4, 5 ascending order. So we would say that in this case there are 4 inversions. So there is another way to picturize this if you like. So you can actually write down these two sequences, your sequence and your friend's sequence, as 2 rows of numbers. So 1, 2, 3, 4, 5 is your sequence, 2, 4, 3, 1, 5 is your friend's sequence, and you connect the number on top to the corresponding number on the bottom. So you connect every pair j, j. So 1 is connected to 1, 2 is connected to 2 and so on. Now notice what this means. It means that 1, 2 and 2, 1, if I look at these two lines, it means that they are in the opposite order below because they should be in the same order. If they are in the same order, then the lines will be something like this. Right? They will not cross, because if 2 comes after 1 on the top, 2 will also come after 2 on the bottom. Then the two lines connecting 1 and 2 to the bottom 1 and 2 will not cross. They will kind of go down without meeting. Whereas if they do cross, like this case, right, that means that 2 has somehow jumped before 1. So every time you see a crossing, you will see an inversion. So just as we saw there, we will see that we have these 4 inversions. So this is the 1-2 inversion, the first one, right? This is the 1-4-4-1 inversion, is this one, right? Then we have the 1-3 inversion is this one. Sorry, the 1-4 inversion is this one, right? And the 1-3 inversion is this one, and the one on top is the 3-4 inversion. So we have 4 inversions represented by 4 dots. So it's not very important which one you choose, but the point is that if I do this the way we did it now, and we are checking for every pair I comma j whether j has been pushed in front of I, then we are effectively checking order n squared terms, and we are computing for every pair whether it's an inversion or not. So we are explicitly counting the inversions by observing them, and so this is going to take order n squared, because there could be order n squared inversions, and we are checking every pair by brute force. So the question is whether we can do this more cleverly. So since we are talking about divide and conquer, obviously we are going to do this by trying to split this sequence into 2 parts. So we have, your friend has given you, so remember that our permutation is always 1, 2 up to n, right? So we have a fixed ordering, and with respect to this fixed ordering, our friend has a different ordering which is given by this permutation I1, I2 up to In. Now we want to count the number of inversions between our ordering and this new permutation. So what we do is we divide it into 2 lists of size half, right? So we go up to n by 2, so I1 up to In by 2 is the left list, and In by 2 plus 1 up to In is the right list. So we break it up into 2 parts. This is very similar to what we would have done in merge sort. We take the first half and the second half. Now within this, by dividing and conquering, we assume that we can recursively find the solutions, right? So we can count how many inversions are there within I1 to In minus 2, n by 2. And then we know how many inversions there are in the second half between In by 2 plus 1 to In. But this is not the only source of inversions, right? Because there could be inversions which involve some number I here and some number j here. So there could be inversions across this pair which will not be captured in this recursive solution. So we need to add those back, right? So we need to add the inversions across the boundary between L and R. So the inversion here is something where, remember that L is the smaller list and R is the bigger list. So it is something where the smaller list has a number which is bigger than the bigger list. So I is on the left, j is on the right, but I is bigger than j. Right? So the number of inversions across this boundary is the number of such pairs. Pairs where the left hand side is in L, the right hand side is in R, and the left hand side is bigger than the right hand side. So therefore our task to complete this divide and conquer solution is to do this efficiently. So this is our combination phase. So remember that divide and conquer consists of 2 parts. Divide the problem into subproblems that are disjoint, solve them recursively. That is phase 1. So here the division is easy. You just take the first half and the second half. Phase 2 is you take those solutions and put them back together to form a solution as a whole, and this you have to do efficiently, right? So we don't want to again fall into this trap of comparing everything on the left with everything on the right and checking which is an inversion, because everything on the left is n by 2, everything on the right is n by 2, so again we will end up checking n squared pairs, right? So we don't want to do that. We want to do something more clever than that. So how do we count the inversions across the boundary? So one way is to assume that there is something a little bit more structured in L and R. So L and R right now, as given to me, are the 2 lists of preference of elements as ordered by my friend, split in the middle. But what I can do is I can structure them by arranging each of them in ascending order, for example. So what I am going to do actually is to do more work than I need to do, right? All I need to do is count inversions, but in the process of counting inversions, if I actually sort the list, it will help me to do this inversion counting cleverly, because I will just use a version of merge sort where I count. So I am going to adopt merge sort, and I am going to have a stronger merge sort which not only sorts by using the merge sort procedure, but also while sorting counts, right. So I am going to write a version of merge sort which sorts and counts. So I will call it sort and count. And in order to sort and count, I need to count somewhere, and that count is happening at this point. But what is this point? This is point where I am taking the left and the right and I am merging them. So what I am going to do is adapt that merge procedure of merge sort to actually count inversions while merging. So by counting inversions while merging, while I am sorting, I am also simultaneously keeping track of how many inversions there are, and recursively I will add up all these inversions and get a total count as a part of the byproduct of the process of sorting. So let us look at how merge and count would work, right. So merge and count will take these values, say, let me say that this is 137, right, and now this is 268. So supposing this is my left and this is my right. Okay. So remember what happens now. I want to check how many things on the left are bigger than things on the right. So I want I in L, J in R, such that I is bigger than J. This is an inversion. Right. So this is, for example, true of the numbers 3 and 7. Right. So 3 is bigger than 2, right, and 7 is bigger than both 2 and 6. So between 3 and 7, I actually generate 3 inversions, because 3 is bigger than one element on the right. So 3 2 or 2 3 is a pair which is inverted, and 2 7 and 6 7 are both pairs which are inverted. Right. So how do I discover this? Well, if there were no inversions, right, if there were no inversions, then I would enumerate everything in L before I enumerate R. When I am merging, remember, I am picking out the smaller of the two elements at the top and pulling it out. If everything on the left is smaller than everything on the right, then I will first exhaust L and only then move to R. So if at any point if I pick out something from R before I pick out something from L, that means I have discovered an inversion. There is something still left in L which has been overtaken by something from R, right. So we will count the inversions while merging, which is that whenever, as I said before, so let us draw that example again. So we have 137 and 268, right. So now when I am merging, I first pull out a 1 and I say this is fine. Now when I pull out a 2, right, it has overtaken some elements in L. How many elements in L? Well, everything which is in L at this point should have been enumerated before 2 if there were no inversions. So I can directly keep track of the position I am in L and subtract it from the length and say that, okay, now I have got 2 inversions because of this 2. Now I get 3, but if I take from the left, there is no problem. Every time I take from the left, I have no inversions because I am supposed to do left before right in the non-inverted case. Now next number to pull out is 6, right. So when I pull out the 6, again I look at the left list and I see how many elements should have been coming before this, or how many elements 6 has overtaken. So it says +1, right. Now then after this I pull out 7, and then finally when I pull out 8, I do the same check, but now the left list is empty, so I get nothing. Right. So in principle, every time I pull out something from the right list, I have to look at the other list on the left and see how many elements are left, and all those elements have been overtaken. So that must be added to my count, right. So this is what it says. So whenever we add some number im from the right side to the output, then im is smaller than everything which is currently in the left list. So it is inverted with respect to all of them. So I must add the current size of L to the inversion count. So this is the old merge procedure which has now been enhanced to keep track of this count. So the new thing here is that we have this count variable which is initialized to 0, right. So we are assuming now that A and B are sorted lists. So when we are merging, we are going to count the inversions in this way, right. So every time I pick from the right, I must add the length of the left. So remember, the length of the left is m, which is its total length, minus I, because this index I is passing through the list A and the index j is passing through the list B. So when I have finished L and I am only picking from the second list, in principle I will be adding, it's like that 8, the last number 8 which I pulled out, it happens after I finished everything in A. But at that point there are no inversions, so I just append one more element from B and I increment the counters, the pointers inside B and C as before. Whenever I pick from A, there is nothing to be done because no element from A contributes to the inversion. Likewise, if the first element is smaller in A than in B, there is no problem with this thing. Okay. But here when I pick something from B, right, then I must not only move the pointers J and K, the respective pointers inside B and C by 1, but I must also update this count. So I must take the count and update it by m minus I, because m minus I is the current length of L. Right? It's what is remaining in L after I have processed I elements. Right? So n is the number of elements I had to begin with. I am at position I, so 0 to I minus 1 has been processed, so I elements are gone. So the remaining n minus I elements, m minus I elements are inverted with respect to the current P element. So that's the only change I need to make. Keep this count and increment it every time I pull it out. And of course now this merge and count must return this value. So in addition to the merge list, it also returns a count of how many inversions it observed. So once we have done this, it's a very simple matter to employ this in our merge sort to make it a merge and sort, right. So we have a sort and count, right. So sort and count is exactly merge sort, except that I recursively assume that sort and count returns the sorted list and the number of inversions in that sorted list. So this is the divide part, right. So I recursively sort the left and I see how many inversions are there within the left. I recursively sort the right and see how many inversions are there within the right. And now I do this merge of L and R, and this returns the overall sorted list, which is what merge sort is supposed to return, but it also returns these crossing inversions, how many inversions were observed while merging. So now the total number of inversions that merge sort has discovered is those inversions completely on the left, plus those inversions completely on the right, plus these inversions that the merge procedure discovered. So this is the total number of inversions that merge sort returns along with the sorted list. So this is how we use this counting of merge along with sorting to keep track of the total number of inversions in our whole list. So obviously, since this is very similar to merge sort and there is really no extra work that is happening except for keeping track of this count variable and adding 1 to it at every point, the recurrence is going to be very similar, right. If I have a trivial list, then I return in constant time. If I have a non-trivial list, then I have to solve each half of it, so 2 times n by 2, and I spend order n work in the splitting and merging operations. I don't do any more than order n work. The merge is still the same, because remember that when I have to increment the count, I just keep track of that length which is remaining and just add a number. I don't have to scan anything one more time. So obviously if we solve this, we will get T of n is order n log n, which is exactly the same as merge sort. So the thing to note is that we are not claiming that the number of inversions is reduced, right. So we earlier said that the number of inversions could be as low as 0 if they are identical lists, or it could be as high as n into n minus 1 by 2 if every pair of preferences is inverted. So there could be order n squared inversions. Now when we did a brute force algorithm, we were counting them one by one. We were looking at every pair ij and deciding whether it's inverted or not. So if there were n squared inversions, we would actually examine n squared elements. Even if there are not n squared inversions, we have to examine every pair of elements to determine whether they are inverted or not. So we are kind of enumerating the inversions one by one. Whereas here, even if the number of inversions is large, we are doing it in chunks. So if you go back to that merge and count, see at this point, the count increases by a chunk, right. So if there are lots of elements that this current value b of j is inverted with, it will add all of them without going through each of them and saying, oh, I am inverted with this, I am inverted that. So we are not explicitly examining every inverted pair. So we are not going to for example, one of the things we do not get from this version of the algorithm is what we did earlier, right. So when we first solved this problem, we got this explicit list of all the inversions. That was a byproduct of the brute forcing is an explicit listing of all the inversions. We don't get an explicit listing. What we are getting is the number of such pairs, right. And if you are asking for this recommender system, that's what we want. We want to know how similar two people are. We are not particularly concerned about which movies they disagree on. We want to know how many movies they disagree on. So we just want the count, right. So by doing this divide and conquer, we are solving the problem in a slightly a weaker way in some sense than the brute force algorithm, but this is what we want. We want the count, we don't want the list. The list could be large. If you want to enumerate the list, you have to do order n squared work. But if you just want the size of the list, you can do it in order n log n time.